The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
One of the things that Per was interested in before he even started with the silica fume and looking at the chloride profiles was marine concrete, because it was one of the things he was investigating, and that led him, obviously, when he had the chance, to push this marine environment and high durability concrete, as we'd heard from a number of the presentations now. I'm going to look at the Storebaelt link, which is one of the biggest bridges we did a long time ago, and Per was very involved in the work that was going on with that. We're going to look at that and then see how that has progressed forward through developing that high durability concrete for the marine environment. This is where the Storebaelt is actually sitting. It's in the middle of Denmark. It's right through the center of the Great Belt, which is the waterway that goes through. You can, thanks to Google Maps, it's always nice to be able to get a picture, and you can see it. It is that big to be able to see. It doesn't look very much in that, but you'll see when we talk about the distances involved, they're quite big, those bridges. What were the project parameters? Well, they wanted to eliminate ferry traffic, if they could, because the journey time on the ferry was 1 hour, and that was for everybody getting across from one side to the other. They wanted to greatly increase that traffic flow to make a fast road connection and, of course, a full rail connection, because they could get people onto the public transport. It would cut down a lot of the work on the ferries, and it would increase the connection time so people could actually live and work on both sides of Denmark. They wanted a permanent, long-term link. This is all becoming part of the European road network. So the idea is that you'll be able to drive around the whole of Europe on what they call E18, E-roads, E-numbered roads, and you'll be able to go all around Europe and be able to get everywhere. And of course, if they get this right, you can go everywhere without doing a ferry trip anywhere. By permanent, they meant a minimum 100-year design life. That's no major maintenance on that structure at all. Yes, possibly painting it in a few places or redoing surface areas, but no major maintenance. So this was just part. This is a very small part of the material specification. You can imagine that on a project that's going to be this big and last this long, they're going to have a lot of qualifications for it. You notice that we still didn't get away from sulfate-resistant cement. They still insisted on having sulfate-resistant cement in there. But a maximum heat of hydration. They were concerned that they wanted to keep that heat down. Interestingly, you'll notice that the fly ash is 25% on the 45 micron sieve there, which is a lot higher than the ASTM value for it, but you'll notice that the 4% is actually less. This is quite considerable. And in terms of the silica fume, the maximum 10% is easily passed, but the loss on ignition relative to the ASTM standard for silica fume is actually 3 times lower than the ASTM standard level for loss on ignition. They were pushing for really high quality materials to build this bridge. A lot of qualifications for the gravel, as you can see, stratification, absorption, but they were looking at how they were going to pack that concrete. And again, we come back to particle packing and software for this sort of thing, but they weren't using the software, but they were going for cubical grains. They realized that they couldn't have the flaky grains. They couldn't have the elongated grains. They needed cubical grains to make sure that they got a dense, good body on that concrete. The sand, they were concerned about alkali aggregate reaction and alkali expansion, as you can see. There are 2 different mixes. We'll come into that in a second. Mix A, Mix B. Maximum 1% mica in this mix. So that was just a small part of the material specifications. Then we've got the concrete specifications. Design life 100 years, as we said. 50 megapascal strength. Not high strength, but the durability was the considerations here. Mix A, Mix B, you can see 0.35 water binder ratio. But the interesting part is that you've got a maximum of 135 kilos of water. So it's not just the water-binder ratio, there is a maximum amount of free water in that concrete. This has been broached a number of times by people looking at durability. Mix B was a less severe exposure area, as we know, if you're in the water or in the tidal zone, as opposed to the splash zone. Minimum cement content 300, we still couldn't get away from minimum cement contents, but as you can see, the fly ash content was a minimum 15% of the total, silica fume range between 4 and 8, but the pozzolanic blend was 25% of the total binder. This was the target that they wanted on the pozzolanic materials in that mix. So then we had a few more parameters for the concrete. You can see the air content, maximum 20%, but minimum 8% of the paste volume. This is the entrained air, of course. But the entrapped air, maximum 7%. The specific surface of that air, 25 square millimeters per cubic millimeter. Chlorides. This specification has caused us more headaches over the last few years than anything else. This was the first time that 0.1% chloride value of total powder came into existence. And ever since, we've had people specifying 0.1% chlorides in these types of concretes. It's very difficult when the maximum value you have in the product is actually 0.3. So it's a very difficult thing when somebody specifies something and then it rolls on in the cut and paste that we've seen in standards and specifications throughout the years. Alkalis, 3 kilos, the low level of alkalis there that they wanted in that concrete. As we said, there were 2 basic mix designs, but they used 3 different blends of the cementitious mixture. You can see for the East Bridge, the tunnel segments, and the West Bridge. The East Bridge actually was the high bridge, the West Bridge is the low bridge, and you'll see how that goes as we progress through the pictures. But again, very similar combination in those mixes, just a few little tweaks here and there in that cementitious component. And you'll note that it's not a high cementitious value. We're still in that region of 400 kilos Portland and blended cement in that mixture. The low bridge, this is the West Bridge. This is 2 bridges. We call it 1 bridge because it is actually connected together in various places, but a small bridge for the 2 lanes of rail traffic and a larger bridge for the dual carriageway for the roads. You can see the 6.5 kilometers. So when you saw that tiny picture, that Google picture, and you saw the road coming out, the bridge coming out, that's actually 6.5 kilometers long. Passage height is 18 meters. They don't expect the main traffic, the shipping traffic, to go through that. That goes under the high bridge. Concrete volume, 430,000 cubic meters just for those 2 bridges. Standard design, box girder type. Here you can see it in operation there where they were putting it down. You saw on the last picture the Swan. This is the Swan. This is a specifically built boat that they now use on most of these bridges. It actually got sent around the world to do the East Sea Bridge in Shanghai. It was that important a vehicle that they took it all the way around from Denmark, right the way through and round the back, down and out to Shanghai to do the bridge down there. As I said, it is joined together. It is only 1 bridge. It's joined together by little bits of metal every now and again. Train line and the road line on that side, as you can see, nice and open, nice and clear. And the railway tunnels, 2 separate tunnels, obviously, one going forward, one coming back, and 62,000 precast concrete lining elements. When they started the project, he was a boy, and he's now grown up, and he's still moving a few of the old segments that they have left around. 8.5 kilometre long, these subsea tunnels. They lost one of the tunnel boring machines whilst it was doing it. It went off sideways, and rather than dig it back out, they just left it there. So they had 2 boring from either end, and 1 got lost, so they had to bring in another one. So they bored 2 tunnels with 5 tunnel boring machines. And 25,000 cubic meters of concrete, then obviously the backfill that surrounded it. Very big project. Yes, there is, as you can see, there's a membrane layer on that concrete as well. They weren't going to take any chances with this. The whole point was that it's going to last 100 years, even in that subsea environment. The island junction is quite an interesting place. Here you can see the road going out. This is the twin bridges going out to the island, Sprøga Island. The island is now 4 times its original size. but they weren't allowed to build on it until they had sorted out the environmental problems that they were going to have there. They had to leave room for the colony of indigenous green frogs. This is what we have to do in building some of these bridges. If Mike was still here, he'd tell you some of the bridges you build where you have to look at where the flow is going so that you don't disturb the animals and the environment. There's an indigenous colony of green frogs on that island. They're still there. Here you can see where it reaches. So this curve goes out, and that's the curve coming back in. I did try turning the picture upside down, but it looked wrong because the cars would have fallen off the bridge. The tunnel, as you can see, the tunnels go down into the main island, so that's where the train goes down through there, and the cars come over the main bridge section. The reason they didn't take the train through the bridge, as has been done on later bridges, is because the distance is actually too far for them to bend the rail track. So they couldn't actually run the rail through the middle of the bridge. Talking of the high bridge on the eastern side, here you can see the run of it. The free span is 1.6 kilometres between those two uprights. When you are out on the water, the distance is so much that the towers are completely perpendicular, so they're straight up and down relative to the earth. But when you're out there, you can look at them and they actually taper away. The distance is so good that you can actually see the taper on the top of the towers. For those of you who are interested, this anchor block, to give you a comparison of the size, as you'll see a picture in a minute, that's the size of a football pitch. Oh, sorry, that's the size of a soccer pitch. That's for those of you who don't play football by throwing it around. Soccer pitch size inside that anchor block. That's how big that concrete block is. Just give you another shot. That's inside one of the anchor blocks looking up underneath. Here you can see the cast and climb bit as they ran the bridge out and they ran it up. 65-metre clearance so they can get the cruise ships through underneath and really improved that turnaround time on that project. Huge project, 1.06 million cubic metres of concrete. As you saw from the mix design, we were talking about a triple blend all the way through, fly ash and silica fume, every cubic metre of that concrete. When I started doing this, I thought it'd be great. There must be some numbers for this now. Because we're going to talk about how good it is. There must be some numbers for it. And Ben and myself searched every database we could possibly find. We did the inevitable Google, and we found papers and papers and papers about designing the mix, but I couldn't find anywhere that actually gave us numbers for it. So I do apologize for that, but we're here to talk about Per's legacy and some of where that went. And the reason was, we were looking at this on the marine research. He was involved in that particular concrete. They did have some problems. He went down. We got those problems sorted out. They developed on those mixes. That research and the development of those mixes led to major use of binary, ternary, and quaternary blends on some of the major infrastructure bridges around the world. Now, the durability and the lifetimes that they're now producing these concretes through, these stand as a statement to the work that Per initiated and worked on, along with respected colleagues, many of whom are in this room, and they've continued to develop these mixes and look at these high durability concretes. And I want us just to see where that took us from and led us to in the development of these concretes. Here you can see the next bridge that they did in Denmark. So they took the Storebaelt from the middle and they went across here because they didn't want to have a ferry trip to Malmö, because Malmö is where a lot of people who work in Copenhagen, they live in Malmö. So they were catching the ferry backwards and forwards. It's cheaper to live in Malmö than it is to live in Copenhagen. So they were crossing every single day. So they decided that they would build about 15 kilometers of connection, a tunnel, an island, an upright bridge to get people across, all the way across. Now again, believe it or not, what do we have? 100 years service life, 100 years without maintenance, low alkali cement, water cement ratio 0.4, crack width, yes, we now had a specified crack width, 0.2 millimeters. High quality aggregates, as we heard, if you've got high quality aggregates and you can wrap them up in that silica fume concrete, that blend, it will give you high durability and high resistance. The Danish side is the triple blend, the same as they used on the Storebaelt. But on the Swedish side, they don't have fly ash and they don't have slag. So they just used a binary blend with 5% silica fume. And this was nearly 2 million plus cubic meters of high-performance concrete. You've got to admit, that is a pretty spectacular bridge. Very high clearance for, obviously, the ferry and shipping loads going through, but a very smooth, very even road for crossing. This one you saw this morning, those of you who are here, just to go through it. This one, they could actually run the train through. And when you're trying to get out of Hong Kong and they shut the bridge down, there is no other way you can get out of Hong Kong anywhere else. And you're stuck if they shut the bridge down. The train goes through the middle of the box girder section. Box girder section was precast, but the towers, 80 megapascal concrete, a 390 mix, 30% Portland, 65% blast furnace slag, 5% silica fume. The development of these triple blends being used in this particular mix. This was a slag version. The towers that you can see in the background here and the lead-ups were the fly ash blend, which was 25% fly ash, 5% silica fume. And we progressed to other parts of the world. We went round to India, and India was very keen to adopt high-performance concrete. Most of their stuff is done at 10, 20, 30 megapascal. When I first went there, they said, we don't do 50 megapascal concretes. We only do 40 if it's really, really important. 30 megapascal is what we use. And that's why things keep falling down, and that's why you keep building flyovers that have meter-wide pillars, and 2 or 3 meter-wide pillars next to each other to keep 10 meters of deck up in the air. So they said, well, okay, all right, we'll work on that, and we'll specify 75. This is a place that doesn't produce 40 megapascal concrete. So they specified 75 megapascal. And yes, this was 2 different blends on this, OPC and silica fume for the high performance ones, the precast areas, for where they wanted a low heat of hydration and a long lifetime, a long open window for the plastic concrete. They specified fly ash as well, because where they were doing these columns, the column bases, the concrete was cast, produced on site. It was then put in a tank on a ship, which when took it out to the barge, out to the casting point, and then they had to pour it out of there and actually cast the piles in situ out in the ocean. Strength and marine durability was required, and they got their 75 megapascal at 28 days. They got a rapid Coulomb test at averaged out at 600 coulombs, and the DIN 1048 test came in at 0 water permeability. Even then, they did the belt and braces, or as you would say over here, belt and suspenders, and you can see that some of the columns actually have paint. They are painted to prevent attack in that splash zone area. Now, it's a very spectacular bridge. You can't quite see it from the other picture, but it's actually 4.5 kilometers long, and this is the view as you come onto it, and you look from the main bridge, the main shipping bridge, down to the fishing fleet bridge. The fishing fleet insisted on their own bridge so they could take the fishing fleet out, and the shipping all had to go through the other one. And it's 4 lanes. This will be 4 lanes of Mumbai traffic at 50 miles an hour maximum speed. Or that's the legal maximum speed. If you've seen them drive in Mumbai in any of the films or pictures, you will know that a straight road that's 4.5 kilometers long with a 50 mile an hour speed limit is like a red rag to a bull. The problem is that that's part of the system that will go round, and there's an actual 90-degree dogleg at the end of that bridge. And we saw this morning, just to reiterate, this is 32.5 kilometers of road bridge. 35 megapascal and 50 megapascal concretes. Again, not high strengths, but high durability was what was wanted. This had to resist a Richter 7 earthquake. It had to resist water penetration. It had to resist chloride penetration from the salt water. It had to resist the 100-year highest wind, the 100-year highest wave. It's right out in the ocean. It had to resist impact as well as thermal expansions. So there was a lot going on about this bridge, and they built it, as we said earlier, in less than 3 years. That quad blend was pre-blended. You had OPC, fly ash, and slag as one triple blend, and then the other quad blend had the silica fume in it. But those 2 mixes of cement were pre-blended off-site. So all you had was 2 silos. You had 2 batches for your cementitious factor. And the interesting thing is this has a 50 mile an hour speed limit. Again, I don't think you really want to risk trying to stay at 50 miles an hour, because I think with that nice big open road that you get quite a few people breaking that speed limit. But talking about limits, if you're going to test something, test it. This is the one thing we all learn from Per. If you're going to test it, make sure you test it. Make sure you test it in real life. None of these silly little tests. Load up all the trucks, every single truck you've got, and drive them over the bridge, nose to tail, and it's still there. It is called the Sleeping Dragon locally, and it is a tremendous structure. And it's that type of development, the concretes, the technology that we put into these sort of projects that has come from all that early work, from him prior to even Elkem and working with silica fume, getting that interest in marine concrete, taking it through, leading us through to this level and this quality of concrete. Thank you.